So hello everyone, in this video we are going to talk about the support vector machine. So this is a new algorithm. So this algorithm is a powerful classifier that works both on linearly and non-linearly separable data. So it does not matter whether our data is non-linearly separable into two classes, it can still create a decision boundary between the two. uh, it can happen in higher dimension. First we will talk about only about the linear case. So before starting off, I would like to request you to please watch those regularization term and cost function term in the from the logistic regression video of my channel of this same playlist. So it uses a cost, this SVM also uses a cost function which is very similar to the logistic regression, and I have clearly derived this cost function in case of the logistic regression, so I am not going to explain it again. So in this you can clearly see that there are two terms C and there will be a term, let's say M also here. So what does this is a weight basically which gives more weightage to the cost function, that is to minimize the error. So what we find is for what is support vector machines? Basically it will create a linear decision boundary. For as of now there can be linear, there can be polynomial also. So as of now we are looking about the linear case, where it will create a decision boundary in order to maximize both of these margins. It will work in such a way that these both margins are maximized. So let's say we are looking onto some decision boundaries. Let's say this figure, both of these boundaries are there, but now our question is that in which cases will support vector machine will make the decision boundary as this black or this magenta color. So now in our cost function if we see, so okay, so this cost one is basically the cost for where y equals to 1 and the cost where y equals to 0, and y0 and 2 are the two classes for this case. And this C, if this C is greater, it means that we are giving more weightage to the cost function, and therefore this our if we, with a very high value of C, our model will tend to get overfitted. So if C is very large, we will get this magenta boundary, but if C is very small, we might get underfitting, but a comparatively smaller value of C is reasonable here because of separating the two classes. And we would like to basically generalize our model and sacrifice this error. So there can be many types of variations, so let's jump into our code. So to give a visual representation, I am just importing the libraries numpy is np from sklearn.svm. We import SVC, which is support vector classifier, and to show you in the graph I am also plotting matplotlib.pyplot as PLT. So we create, suppose we have two features f1 and f2, and 0 or 1 are the basically the classes. So there are four classes of zeros which are represented by this black dots, black or purple dots, and these yellow dots are basically class 1, and these are the coordinates which I have plotted accordingly. Now this svc.linear, we have a function svc.linear which gives us the coefficient and the intercept. So now if you remember the logistic regression function, we also had this similar decision boundary. So this is the equation of our decision boundary, y equals to m1 f1 m2 f2 and m3. Please note that f1 and f2 are the features which are plotted in the graph, and y1 is just the decision boundary. Now if y greater than 0, we will start predicting some value, let's say f1, and if y less than 0, probably we will start predicting, probably not, we will start predicting this class of purple color dots. So to get the exact boundary of y, what we do is, this m1 and m2 are these two, and m3 is this intercept -1. So for y equals to 0, this region is for y greater than 0, and this region is for y less than 0. So we equate this y to 0 to get our distance boundary, and we get f2 equals to minus of f1 m1 f1 plus m3 by m2. So we implement this same equation, this equation we are doing here, -1 of SVC intercept plus linear coefficient 1 into x1 plus linear coefficient of 0, 1. Just match it, and then we just plot this function, and it looks something like this. Now if we do some small changes, like we change this to yellow color and then plot, our distance boundary will be definitely a little bit bent. And then here it was c equals to 1. Now we are changing this c value to 2 to tell our model that we don't want to sacrifice any of our error. So it would plot something like this, which will clearly, which may not be most general, but it gives 100% accuracy on the training data at least. So we can adjust the appropriate value of c. So of course c equals to 2 is not the best estimate here, because uh, for other values it is not general, it is an overfitted graph. Okay, so now let us look at the multi-class classification of SVM. So we can just import our required libraries like SVM, support vector machine datasets, and import numpy as MP. From sklearn.model selection we are importing train test split also, and to plot the graph we are importing pyplot. And for iris dataset we are just creating the x and y and then doing on the split, 10 test split. So 75:25 is the ratio by which training data is to testing data will be splitted, and then we are creating the classifier object handle and then fitting our model. Now we can also use, suppose we use linear kernel, we can also use kernels like RBF kernel, polynomial kernel, sigmoid kernel, and these have some different values. Let's say RBF has values of gamma and c, so we have to check what is the best parameter value of gamma and c that would give us the highest accuracy. So we'll look into that, how to check that. So these are the basically the graph functions. So these codes you may ignore, this is just to show you how the iris dataset, the three flowers of the iris dataset separated by the SVM classifier looks like. Now there is something known as grid search, so let us just see what is that. Before that, be clear that we might go for using other kernels like RBF polynomial and sigmoid kernel. You can search more about these in the documentations, and you can just keep on trying this to see which gives the best accuracy to your given data set. Now there is something known as grid search CV. So what it does basically, suppose you want to use RBF kernel. Now you have to give certain parameters like gamma equals to how much, c equals to how much. So how will you know which value of c and gamma will give you the best accuracy? So you can do one thing, you can put the various values of gammas and various values of c to check which gives you the best accuracy. Or what you can do is grid search. So we have some ready-made functions, ready-made modules. From sklearn.model selection, import grid search CV. So we just do the same trend test split, and then we use, suppose, this RBF kernel, and we see it gives us some accuracy by default. It takes the default values of c and gamma, and it gives us some accuracy. Now we will do grid search CV. So we will create a variable grid, which is basically a dictionary which takes the values of c in a list and the values of gamma in a list, and it will return us which value pair among all these is the most appropriate. Now we create some object known as abc.gridSearchCV and we just fit those objects. Now this best estimator function will tell us that c equals to 100 and gamma equals to 0.005 gives us the best accuracy, and if we use those values of c and gamma we get exactly 100% score, which was earlier 0.947 score. So this grid search CV is very helpful. This 1e2 means 100, 1e3 means 1000, and this minus 3 means 10 raised to the power of minus 3 and minus 4 and so on. 5 into 10 raised to the power of minus 4. So not necessary these, you can take any combination of values, and for seeing that which will give us the best accuracy, you can always do this grid search CV. So yeah, that's almost we have covered our SVM portion. You can try and apply it on various datasets and see how does it do in comparison to logistic regression, how does it do in comparison to the algorithms like KNN algorithm and all. So you can just compare. So yeah, that's all from this video. Meet you in the next video with some different algorithm with some different concept. Till then, thanks a lot.